Hi, Mr. Green here. I'm going to be taking you through the next topic of the energy section of the AQA Physics GCSE, and this is on nuclear fusion. Your learning objective is to know how nuclear fusion occurs. Please pause the video whilst you take that down as your lesson objective. Okay, so we've got 5 retrieval questions for you to start with. Please pause the video whilst you attempt those questions. Okay, question 1. What's meant by nuclear fission? Nuclear fission is when large nuclei are split to form 2 smaller nuclei, and that releases energy. Which 2 isotopes are fissionable? That would be uranium-235 and plutonium-239. What's a chain reaction? Chain reaction is a reaction that causes further reactions to occur, and that increases the products of that reaction. If one of the products of that reaction is energy, it will increase the energy that's given from that reaction. What do we include in a nuclear reactor to slow neutrons down? We'd include a moderator, which is made from graphite. And what do we include in a nuclear reactor that absorbs neutrons so we can try and moderate the rate of energy transfer? That would be boron control rods that can absorb neutrons. Okay, our learning outcomes today are to be able to explain the process of nuclear fusion, to identify the reactants and products in a fusion reaction, and to write nuclear fusion reactions down. Okay, so nuclear fission is the splitting of atoms. We stated that just earlier. So what do we think nuclear fusion is? What does that word fusion mean? What's happening here? We get nuclear fusion taking place here. But what does each part of the diagram represent? We've got protons, neutrons, and that wave is energy. So we've got 2 smaller nuclei which are fusing together to form a larger nucleus. Okay? Nuclear fission is the splitting of an atomic nucleus. So this is what we've previously seen. When this happens, lots of energy is released. A neutron's fired into a large nucleus. That becomes unstable, which splits to become more stable. This then releases energy and some high-speed neutrons as it does so. How is nuclear fission useful? It releases huge amounts of energy which we can transfer into electrical energy. How is it dangerous? It produces dangerous radioactive waste which is really difficult to dispose of, and if we don't control that properly, it can release dangerous amounts of energy. Fission means to split or to divide, so that's why nuclear fission, we refer to that as the splitting of a nucleus. Now, nuclear fusion is the joining of 2 atomic nuclei to form a larger one. The nuclei collide and they fuse together. Now, as that happens, it releases energy. So when we split atoms, they release energy, and when we fuse atoms, they also release energy. So how could nuclear fusion be useful to us? Well, again, if we could harness the energy released, we'd get huge amounts of energy, and that energy would be clean. There's no negative byproducts for that. So how were new elements created in the early universe? Pause the video whilst you answer that. So fusion of smaller elements into larger elements happened in areas where large amounts of energy were present to push them together in the first place. Areas like protostars. So we got smaller nuclei fusing together to form larger nuclei. In order for fusion to take place, we need a lot of energy to kick it off. So we need energy to start that process together, and any places like protostars give us that energy. Okay, so pause the video and see if you can recognize the different elements in that reaction. So we've got 1, 2, 3, 4 nuclei in there. Try and label those. Pause the video whilst you do that. Okay, we start with a hydrogen nucleus, a hydrogen isotope, and another hydrogen isotope. They fuse together to form a helium isotope, which then forms its own different isotope and releases a neutron. Also releases energy. That's deuterium and tritium, which fuse to form helium-5, which then forms itself into helium-4, which is the stable version of that, and a neutron. So nuclear fusion, we get smaller nuclei fusing together to form a larger nuclei eventually. Fusion reactions, we get these nuclei fusing together, and what do we form in this case? If we get 2 hydrogen atoms fusing together in that case, what do we form? That forms a helium nucleus. Hydrogen 1 nuclei fuse with hydrogen 2 nuclei to make helium 3. That's our equation as we'd write it. So when we're writing it as a symbol equation, that's how it's done. At each stage of that process, energy is released. Now this process is used by the stars and the sun to release energy, so that's where their energy comes from. Okay, using that, could we write the nuclear fusion reaction equations for each reaction shown? So write them down with their mass number and their atomic number underneath them. Pause the video whilst you attempt those. Off you go. Okay, you can grab your periodic table if you need to for this, but you should be able to get this done. First one, hydrogen plus hydrogen gives us an isotope of hydrogen plus another isotope of hydrogen with energy. Okay? Second one, third one, and fourth one. So double check your answers on there and make sure you've got those. So how does the sun work? Nuclear fusion is the process by which energy is released in stars like our sun. So as nuclear fusion occurs in our sun, this means the sun fuses hydrogen together to form helium atoms. The sun fuses 620 million metric tons of hydrogen every single second. Our sun is huge. So how do we get all of the different elements? Light elements are formed from fusion of hydrogen nuclei in stars, so that forms elements like helium and carbon. Much heavier elements, further on in the periodic table, are formed when a massive star collapses and explodes, and that gives loads and loads of energy. The debris of a supernova contains all these elements, which can then be pulled together to form planets around stars. So, 3 questions. What's meant by light elements? Why are heavier elements formed when a star collapses? And how are planets formed containing these elements? Pause the video whilst you attempt that. Okay, question 1. Light elements, elements in the periodic table with smaller numbers of protons and neutrons. We'd classify smaller elements as hydrogen to iron, so they're the lighter elements that form. Why are heavier elements only formed when a star collapses? It's because lots more energy is needed to fuse those together. The energy released from a supernova provides this extra energy. Even though it releases energy, it needs energy to kick it off and start it going. How are planets formed containing these elements? The elements are pulled together by the force of gravity to form a disk of gas and dust, which then forms into a planet. Okay, can we identify all the elements formed by nuclear fusion? Use your periodic table to see what's happening on here. Count up the protons and the neutrons, and off you go. Pause the video whilst you attempt that. Okay, for the first one then. Carbon and helium fuse together to form oxygen-16. The second one, that's oxygen-16, which fuses with helium to form neon-20. Neon-20 would then fuse with helium to form magnesium-24. And aluminium-27, which I've given you there, fuses with helium to form phosphorus-31. Again, the neutrons and protons balance each side on that one, so you've got to make sure you've got the same on each side of the arrow. Can we write the nuclear fusion equations for these? So, like we previously wrote, try and write those down using those symbols. Okay. Fusion reactors. We can just fuse small nuclei of elements we have together, and that releases loads and loads of energy, which is great because that then solves our energy crisis. I'm afraid not. But why not? There are massive technical issues we have to overcome in order to build this fusion reactor. In order for nuclear fusion to occur, we need extremely high temperatures to start it off, and plasma, which is a form of energy, must be contained and controlled within a magnetic field. This is really, really difficult to do. Fusion reactors require really, really high temperatures and magnetic fields to control the plasma. So what does a fusion reactor require in the first place? It requires lots and lots of energy. So in order for nuclear fusion to be worthwhile, what do we need from it? Pause the video whilst you work that out. What we'd need is more energy given out than we put in to make the nuclear fusion happen. We need a net gain of energy, otherwise it's not worth doing. Now, scientists have been working on experimental fusion reactors since the 1950s, but currently we can only sustain it for a few minutes and no longer, so it's not a viable source of energy at the moment. Research is still continuing into those. That's the inside of a fusion reactor. But if we can really push that on, we could do really well to get nice sources of clean energy. But at the moment, we can't sustain it very long. What's the potential benefits? Well, there's no radioactive waste produced. We only produce helium, which is harmless. It's clean energy, so we get no greenhouse gases released. The fuel is readily available as heavy hydrogen naturally occurs in seawater, so we can get that very easily. And also there's a really low fuel cost. Any deuterium we require, which is that heavy hydrogen, can be distilled from seawater. And tritium, we can breed that in a reactor, so we can make the fuels that we need quite easily. So fission versus fusion. Let's try and do a table comparing them to each other. So with fission, we produce harmful radioactive nuclear waste. It's got to be securely contained and stored for decades, and it requires radioactive material that's a finite resource found in certain locations. Both fission and fusion, and fission's already used to meet our energy demands. Both fission and fusion release energy to generate electricity, and there's no burning of fossil fuels, so neither of them release atmospheric pollution. Fusion, we don't get any radioactive waste produced, and helium is harmless, that's the only product. The fuel for fission is really readily available because heavy hydrogen occurs naturally in seawater, but currently it's not a viable option for generating electricity due to the large amounts of energy we need to kick it off. Okay, 5 questions there for you to attempt. If you could pause the video and attempt those. Off you go. Okay, question 1. Explain how the process of nuclear fission and fusion are different. Nuclear fusion joins light nuclei together, and nuclear fission splits them apart. 2a. What are the major issues with nuclear fusion? We need huge amounts of heat required and magnetic fields to contain that plasma, and that's a huge energy requirement to do that. Why is the amount of energy required for nuclear fusion an issue? Because if more energy is used than is released, then it's not economical, so we can't use that as an energy resource. We need more energy out than we put in. Okay, write an equation to show the fusion of a proton with a hydrogen atom, which has got 1 neutron and 1 proton, and the resulting product. That would look like this. 1,1p plus 2,1h gives us 3,2he. Complete the following nuclear fusion equation. That's how it looks completed. What conditions are there in the sun which allow nuclear fusion to occur? It's got really high temperatures, so the core is made up of plasma, so the conditions are all there for it to happen. How does fusion occur in the sun? Plasma consisting of nuclei which don't have electrons move around with a great deal of energy, and they collide together, fusing together, and that releases further energy. Okay, hope that was useful for you all. Please have a look at our other videos that are available on the YouTube site. Thanks very much for listening. See you soon. Goodbye.